Okay, a new problem. So we're now onto kinematics. So the beginning of kinematics is a bit strange, really. It's average acceleration, average velocity stuff. It kind of looks a lot more complicated than it is. When we get some integration done and we do the proper kinematics, it'll be a lot better. But nearly all of it, it's about this motion kind of on a straight line. So probably not particularly useful for this. But when we look at the next example, that will make a lot of sense. So a particle moves in a straight line with displacement given as s of t, so as in the displacement as a function of time equals 3t minus t squared. So s is distance from the origin. We've got this straight line kind of motion, and this might be the origin. S is literally for any moment in time. If you're to the left of it, you're negative. If you're to the right of it, you're positive. But when it talks about motion, it's only along the line like that, and I think that's probably going to be the case with all of your kinematics in the IB will be about motion forwards and backwards along a straight line. Anyway, we've been asked to find the average velocity for the time interval from t equals 2 to t equals 5. So velocity is literally distance over time. So if all you've got is the end position and the start position and the two time intervals, you're going to do the difference in distance divided by the difference in time. So we're going to do average velocity equals, so it's going to be we're going from 2 to 5, so it's going to be s5 minus s2 over, so that's the difference in displacements between at time 5 and time 2 over the difference in time, so literally 5 seconds minus 2. So s5 is where you substitute into here, so it's 3 times 5 minus 5 squared, and then minus s2, we're going to need a big bracket for that, so 3 times 2 minus 2 squared all over 5 times 2 is 3, so that equals, so 15 minus 25 is minus 15 minus, sorry, 15 minus 25 is minus 10. Minus, well, 3 2s are 6, 2 2s are 4, 6 minus 4 is 2, so minus 2 over 3. Minus 10 minus 2 is minus 12. Minus 12 divided by 3 is minus 4. So that equals minus 4 meters per second. So ms minus meters per second. Okay, now part B. Actually, I'll do that on a different bit because I've got to rub this out. Okay, so for part B, you've been asked for the average velocity from the time interval from t equals 2 to t equals 2 plus h. So you've got kind of t2 equals 2 plus h, and t1 equals 2. So you do the same thing. You're going to do st2 minus st1 all over t2 minus t1. So the difference in displacements over the difference in time. So remember, s of t equals 3t minus t squared. Don't forget that. So average velocity equals, you put in 2 plus h, which is the t2, so it's 3, 2 plus h minus 2 plus h squared minus, and you're subbing the value for 2, which I probably, if I hadn't rubbed it out, I could remember what it is, but never mind. Minus 3, 2 minus 2 squared all over, so 2 plus h minus 2, which you see will cancel nicely into just an h, so equals 6 plus 3h minus, so this is going to be 4 plus 2h plus 2h, so 4 plus 4h plus h squared. Right, that should have a bracket around it, shouldn't it? Right, so this is 3 2s are 6, 2 2s are 4, 6 minus 4 is 2, and it was minus 2. That's how I remember it now. Minus 2, all just over h, right? So that is equals minus h squared when we distribute this bracket a bit. And then you've got 3h minus 4h, which is minus h. Then the numbers, you've got 6 minus 4 minus 2, which is just 0, very handy, over h, which you could just divide through by h, but personally I'd like you to sort of show it like this, that equals h. You can pull a minus h out if you like, but I'm just going to take an h, and then you've got minus h minus 1 over h, and you can whip them off like that, so it equals minus h minus 1 meters per second. Okay, now in part C, we've been asked to find the limit as h approaches 0, should ring some bells already, of s2 plus h minus s2 over h, right? So if you recall from part B, this whole expression we were asked to simplify, which went to minus h minus 1, so equals lim as h approaches 0 of minus h minus 1. So as h approaches 0, you can basically just ignore that. So it equals minus 1 meters per second minus 1. So, sorry, meters second minus 1 meters per second. So comment on its significance. Right, so the significance, this is the definition of the derivative at the point A. So you might remember, so the lim as h approaches 0, f of a plus h minus f of a all over h gives you f dash a, as in it gives you the rate of change of the function at that particular point. We're interested in, this is the point 2, a being 2 here, so the rate of change of speed is velocity, right? So that's telling you at 2 seconds, so when t equals 2, instantaneous, I still can't spell instantaneous, come on sir. Equals minus 1 meters per second. So the 1 means it's travelling at 1 meter per second, and the minus means it's going that way, it's going to the left. So if you look upon the line of motion with some kind of origin here, you know it's going this way along the line. And we'll do a lot more about that in the coming examples and questions.